the Seebeck still goes up, but then of course the sigma. So it's a trade-off in that case.
Okay, but it's not. It's very tough to. Yeah, it's okay. 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 This is, yeah. I want to use it. It's okay. So thank you very much to the organizers for inviting me to this nice workshop in this nice place. I'm going to talk about electron systems. Most of the talks before were based on phonons as carriers of the heat transport. But in my case, I'm going to talk about the interplay between charge and energy transport in electron systems in the quantum regime and also under the effect of driving AC fields. So this work was done in collaboration with these people, Florencia Ludovico, who is right now a postdoc, that at the time of the work was PhD student, two postdocs, Francesca Batisca and Javier Romero, and three collaborators, Michael Moscalets, David Sanchez from Spain, and Felix von Oppen from Germany. Before going to tell you our work, it is our theoretical work, I'm going to mention some experimental devices which motivate this sort of studies. The first device I want to mention are the so-called quantum capacitors or single particle emitters. These are devices constructed in systems under the quantum Hall effect. In the quantum Hall effect, as you know, the quantum Hall effect supports edge states in which electrons propagate chirally and with the perfect conduction. And experimentalists managed to construct these constrictions by recourse to nanolithography. And with this, in this way, they construct these so-called point contacts, and also manage to construct this small island which behave as quantum dot. The electrons in this part are strongly confined, so we can regard these electrons are in this quantum well with the discrete levels. These systems are manipulated by AC gate voltages in a way that this, so the gate voltage is applied at this region, and in this way the levels of within the quantum dot are moved up and down, and in this way they manage to use these setups as particle emitters. So when you move these levels and you put one of these levels up the Fermi sea of the rest of the structure, one electron can be injected into the Fermi sea. There are also ideas of extending this and constructing this sort of devices in other systems supporting edge states, and the paradigmatic and interesting case is the quantum spill Hall system, which instead of supporting just one chiral edge states contains two edge states made of Kramer's pairs, in which one of the spins propagate in one with one chirality and the other with the other chirality. Most of the studies in these systems are focused on investigating the behavior of the charge transport. But there are already some few examples of investigating also the behavior of heat transport, and this is one of the example. This is one example in which also in a quantum Hall device, it was measured the thermal conductivity, and it was proved that this thermal conductivity is quantized and has this behavior which corresponds to exactly one electron channel. The other example, also in quantum Hall devices, is this one in which the chiral propagation of heat was proved. This is a quantum Hall setup. This is the sketch of the edge state. The sample is heated at some point, and the local temperature is determined at 2 points of the structure, and what is proved here is that the heat flow goes in the direction of the charge flow. It means it propagates chirally. Other systems which are relevant and motivating for our theoretical studies are these sort of systems where some small structure like this suspended nanotube is treated by a current, and there is a strong coupling between the vibrational degrees of freedom, the mechanical degrees of freedom, and the charge flowing there. Let me say that the interplay of charge, heat, and work is precisely the central topic of thermoelectricity. As we know, the conventional thermoelectricity, this was already mentioned in previous talks, and there will be several talks on these subjects along the workshop. The main topic of thermoelectricity is precisely to convert electrical work into heat flow and vice versa. The typical setups are sketched here, where in this case we have some current injected in the device, and in this way some cooled part of the sample is cooled. So this is the typical work of a refrigerator. We use electrical work to extract heat from cold to hot place. And the other way around, we have a heat engine in which we have the heat flow from the hot source to the cold source to produce electricity, to produce electrical work. So this is the typical thermoelectrical setup, and this operates in DC. I mean, all these currents and voltages are purely continuous. From the theoretical point of view, the theory in linear response for thermoelectricity is very simple, and it can be formulated on the basis of these two-terminal setups, two-terminal setup in which we have two reservoirs connected to a central conductor. At these reservoirs, we apply a difference of chemical potential, and we can also apply a difference of temperature. And in this way, we have a heat flux from the hot place to the colder one, and also an electrical flow. In order to formulate the theory, we have to take into account some fundamental laws. The first fundamental law is the conservation of the charge and the conservation of the energy. So it says all the charge leaving the left reservoir have to be injected into the right one, and the same thing happens with the energy. In linear response, we assume that there is a linear relation between fluxes and affinities. The relevant fluxes in this device are the charge flux and the heat flux, and the affinities are related to the difference of the chemical potential and the difference of temperature. These coefficients here are coefficients that receive the name of transport coefficients. Here, these are precisely related to the Seebeck, to the conductivity, and to the thermal conductivity. And in linear response, it is important to recall that these coefficients are evaluated in equilibrium, so they obey micro-reversibility, and because of that, they are not independent, but they are related by these Onsager relations. To go ahead with the theory, we have to work with the expression for the entropy production in this device. The entropy production in this device is the heat generated in the left reservoir divided by the temperature of the left reservoir, plus the same thing for the right reservoir. Now we insert in the expressions of the heat current, we use this linear response relation, and we can express this rate of entropy production by recourse in this form, which is bilinear, in the relevant affinities. In order to satisfy the second principle, we know that these transport coefficients must, on top of obeying these Onsager relations, must be positive, the diagonal ones, and also the determinant has to be positive. So this imposes further constrictions for the coefficients, the transport coefficients there. And now we are in the position of getting explicit expressions for the efficiencies. In the case of the heat engine, the efficiency is always what we get divided what we have to invest. In the case of the heat engine, what we get is electricity. This is the electrical flow, and we inject heat. So this is the efficiency. The second principle imposed this boundary. It has to be smaller than the Carnot efficiency. For the case of the refrigerator or the heat pump, we have the other way around. We want to extract heat from the cold reservoir, and we have to inject electrical work. Again, this is bounded by the Carnot coefficient of performance. Taking into account the previous linear relations and also the constrictions for the transport coefficients, this efficiency can be parameterized in terms, also the maximum possible efficiency, if we fix the difference of temperature applied at the reservoir, can be parameterized in this way, where we have here in front of this equation the Carnot efficiency, and this quantity ZT was already mentioned in previous talk, is the so-called figure of merit, which is a function of the transport coefficients. We see that the maximum efficiency, what we could get in any of these devices, which is the Carnot efficiency, could be obtained only in the case of this quantity figure of merit going to infinity. The prototype, the star of the examples for the thermoelectric generators is this one, which is actually used in the space, in a spaceship, in this Mars mission. In previous talks, other examples were also mentioned, but this is the stars. Actually, right now, we are not in position of using these generators at the domestic level, because in most of the material, of the existing materials and structures so far, have a very low figure of merit. So very low means, as in the previous talks, numbers which are smaller than 1, up to 1. 1 would be already great, but this is already very difficult to achieve. And now there is a very important activity to explore going to small sizes, as we heard in previous talk, and also to go into the quantum regime in trying to see if we can improve these numbers somehow. This is an interesting review recently posted by Giuliano and collaborators. In my case, I'm going to explore also the quantum regime, but I'm going also to add the effect of AC driving. And this work was already published in this, and here is the reference. In order to make it clearer, I'm going to show you some classical cyclical devices which I'm going to explore afterwards with electrons. The first classical device is this Archimedes screw, which can be used to pump water against gravity if we invest some work in order to put this screw inside the pipe into movement. But it can also be used in the reversed operation regime if we inject water. With the water, we make the screw we put the screw to rotate, and in this way, we generate work. And this is precisely a motor. The other classical setup is this Stirling machine, which also is a cyclical device. It contains a wheel, and when we inject work to put the wheel to rotate, we can extract effectively heat from a cold reservoir and inject it into the hot reservoir. And the other way around, to use the heat flow from hot to cold in order to put the wheel to rotate, and in this way generate work, and we have a heat engine. So our goals now is to explore precisely these operational modes, but with electrons, with quantum electrons under AC driving. The idea is to extend the previous formulation of the thermoelectrical theory and to propose an appropriate way to quantify the efficiency of these devices. So this is the setup. We have here a conductor, as before, at which we impose a chemical potential, a difference in the chemical potential, a difference in the temperature, or both. But in addition, we also apply some driving with AC forces. We focused on the adiabatic regime. This means that the frequency of this driving is very slow, so the movement is very slow. And for the moment, so we know how to treat, I told you before, how to treat difference of chemical potential, difference of temperature in linear response. The idea now is how to treat, how to formulate a treatment for the effect of the AC driving in linear response. Now, linear response in what? We don't want to make linear response in the amplitude of the driving, but we want to make use of the fact that we will focus on the adiabatic regime, so the small quantity is the variation in time of this time-dependent amplitude of the driving. The scale is the following. The adiabatic, we imagine that the typical time scale for this, the typical period of this AC driving is much longer than the typical time for the electrons to live in the structure. So this sets the scale. So we cannot use a cuboformalism, which is appropriate for small amplitudes in the driving, but we are going to do something in the same philosophy. In this way, we are going to express, to treat, and to approximate, actually, the evolution operator of our system in this way. We are going to consider the evolution operator as a term considering that we freeze the Hamiltonian at the time t, and we treat as if the system were in equilibrium with that Hamiltonian frozen at the time t, plus this correction, which is a correction proportional to the rate of change of the time-dependent parameter. This quantity here is the derivative of the Hamiltonian with respect to the time-dependent parameter, and in what follows, I'm going to refer it as the force. Now, similarly as in a Kubo treatment, if we go to evaluate the mean value at time t of any observable, we are going to have some mean value with the Hamiltonian, or with the density matrix corresponding to the Hamiltonian frozen at the time t, plus now some correction which is proportional to this v dot. Interestingly, what appears here, this coefficient here, what I call lambda, depends on a susceptibility. And this susceptibility is evaluated again with the Hamiltonian frozen at the time t. So it is an equilibrium-like susceptibility. And in this way, but dependent on t, because we freeze the Hamiltonian at the time t, we evaluate the susceptibility. Now, if we add the effect of delta mu, and we can do it as in linear response, as usual in linear response, for instance, using a Kubo treatment, and we put the two effects together, the effect of delta mu and v dot, we are going to have the following relation for the charge flux and for the forces at the time t. This will have some components which correspond to the frozen contribution. This is what we usually call the Born-Oppenheimer contribution, plus some additional contribution which is now linear in delta mu and v dot. And these coefficients here are transport coefficients, very similar to the ones I mentioned at the beginning of the talk. In particular, this coefficient here is the usual conductance. This coefficient here, which relates the charge, flux with v dot, is related to the effect of pumping. And this coefficient, which relates delta mu with the force, is a non-conservative, defines a non-conservative component of the force due to the fact that there is a charge flow, and this coefficient is related to the dissipation. It's a coefficient which gives terms with F proportional to V dot. As all these coefficients are related to susceptibilities with the frozen Hamiltonian, they obey microreversibility and also obey Onsager relations. And we can extend it also to consider the effect of delta t. So I'm not going to do it. Now let's go to analyze the net effect. So now I'm going to focus on quantities which are averaged over one period of the tri-beam. And again, as before, we are going to have this conservation law for the particles, but now the conservation law for the energy changes. We have not only the energy flow into the reservoirs, but we also have some energy flow due to the effect of the AC driving. So this is now the modified conservation law for the energy in this setup. Now we can proceed basically as before, once having the linear response formalism. We have that the power developed by the AC forces is also linear in V dot. We can go to evaluate the net rate of the entropy production. Now we have these three terms. These were the ones that appeared in usual thermoelectrics, and now we have this additional contribution due to the effect of the AC driving forces. We can realize that each of these V dots are proportional to the driving frequency, and so we can identify the driving frequency as the single parameter to identify all the effects of the AC driving. In this way, we reduce the problem to a problem of three fluxes, three relevant fluxes, one for the charge, one for the heat, the affinities delta mu, delta t, this as in usual thermoelectric, but we now have this additional flux for the work, for the flux of work which is exchanged with the AC forces. And what appears to play the role of the affinity related to this new flux is this quantity which is related to the driving frequency. As before, as I mentioned before, these coefficients here satisfy these Onsager relations because they are related to susceptibilities obeying microreversibility. So now let's go to the operational modes I mentioned before. For the moment, let's imagine that we put the two reservoirs at the same temperature, and we just consider the effect of delta mu and the AC driving. And we have, in this case, the operational modes of motors and generators. the case of the motor corresponds to the case where we have an electron flow from the reservoir with upper chemical potential to the lower one. This is similar to the case of the water flowing. And in this case, we can generate work against the AC driving forces. The other way around, when we apply a network with the AC driving forces, we have a generator and we pump electrons from the chemical potential, from the lower chemical potential to the upper one. And in this case, we can proceed as in usual thermoelectric, evaluating, finding the bilinear expression for the net rate of the entropy production, and compute the efficiency. The efficiency, as before, what we get from what we have to invest. What we get in the case of the motor is work. What we have to invest is electrical DC work done by the electrons. And as in the case of usual thermoelectric, fixing delta mu or omega in this case, we can parameterize the maximum efficiency in terms of this quantity, which is a figure of merit, which also depends on the transport coefficients of this problem. And the same thing happens with the case of the heat engines of heat pumps. If we have that the, oops. If we have that the heat flows from the hot reservoir to the colder one, we can do work against the AC forces, and we have a heat engine, and the other way around, if we do work with the AC forces to pump heat from the cold reservoir to the hotter one. Again, we can quantify the efficiency. We can quantify the efficiency as the work done in the case of the heat engine divided by the heat flow. And we can parameterize the maximum efficiency in terms of a figure of merit, which depends on the transport coefficients. So this is a summary of the two operational, actually the four operational modes are mentioned before. And what is important is that in the case of motors and generators, as heat doesn't play any role, we can have an efficiency which is bounded by 1, so Carnot doesn't appear here. While in the case of heat engines and heat pumps, which rely on gradients of temperature, both of them are bounded by the Carnot limit. In any of these cases, the maximum efficiency takes place when the figure of merit goes to infinity. In the case of motors and generators, this means that in order to have this figure of merit going to infinity, this means that we have to get a very low dissipation. This is something usually difficult to achieve. Vanishing conductance, electrical conductance, and pumping. In the case of heat engines and heat pumps, this is achieved again for low dissipation, low thermal transport, and pumping. Okay, we can imagine many examples. I'm going to mention here two. One example is this driven quantum dot working as a motor. This quantum dot is some structure as the one I mentioned at the beginning of the talk, connected to two reservoirs. I'm going to put the temperature the same. It is indicated here a difference of temperature, but I'm going to consider the same temperature for both reservoirs and just different chemical potentials and the AC driving. We have here 3 driving fields, the driving potential, 2 applied at the boundaries of the quantum dot with a phase lag, and another applied exactly in the center of the quantum dot. We don't need this central gate voltage in order to have pumping, because usually to get adiabatic pumping we need 2 parameters. We already have the 2 parameters with these 2. But we include this in order to engineer and the operational mode and to get the maximum efficiency. Depending on these plots indicates, in these plots, I'm showing the different transport coefficients as a function of the mean chemical potential of the reservoirs. And we see that depending on the value of the chemical potential, depending on the value of the chemical potential, we can have the operational mode of a generator or of the motor. In the 2 cases, we can achieve a high efficiencies, very close to 1, in special situations where we have low dissipation and also a minimum of the conductance, as I mentioned before. The other example, more sophisticated, but very, I think, more interesting, is the case of a magnetic island contacted to the helical edge states of a topological insulator. As I mentioned in the beginning of the talk, the helical edge states of the topological insulators have different chiralities, are helical because the chiralities are attached to the direction of the spin. And if without the magnetic island, each of these channels, each of these edges behave as a perfect conducting channel. But the contact to the magnetic island opens a gap in the spectrum. So this is the spectrum of the helical edges coupled to the magnetic island. J is the coupling between the edges and the magnetic moment. And we see that there is a gap here. So we don't expect any conductance, any transport of charge from this side to this other due to the existence of the gap in the middle. However, due to the motor operation, we can achieve perfect conductance from this part to the other. And how does it come? Okay, we can think this as a motor. We are going to regard this M as a large magnetic moment that we can treat it classically. And we can actually derive, there is a way to, starting from the microscopic Hamiltonian, to exactly derive the equation of motion, the classical equation of motion for this, magnetic moment, which is this Landau-Gilbert equation. This is the counterpart of the Langevin equation for the case of magnetic moments. It is a classical equation which contains this potential conservative term. This is the effect of the spin torque. This is a fictitious magnetic field which is induced by the fact that there is a current flowing and that this current supports the magnetic moments due to the electrons, due to the spin of the electrons, and the coupling to this current also generates this damping for this classical magnetic moment. So this damping tends to decrease the prestational frequency. And this is a noise term, as in the case of a Langevin equation. Okay, I'm not going to give you all the details on how to calculate all these quantities, but the point is that we can, given that this equation, we can calculate exactly which is the amount of charge pumped by the rotation of this magnetic moment. And we can also calculate which is the net power developed by this rotation of this magnetic moment. We can apply the previous formalism and to identify here all the transport coefficients. And what we get is that depending on the length of the magnetic island, we can, for islands which are sufficiently large, we can achieve for some values of the chemical potential, precisely the values lying within the gap of the spectrum, we can achieve this efficiency for the motor equal to 1. This efficiency of the motor equal to 1 means that for every rotation of this magnetic moment, we are able to pump 1 electron. In this way, we get, as I mentioned before, a perfect transmission of electrons in a situation where we have a gap, and in principle, without this mechanism, this motor mechanism, we wouldn't expect any current. So I don't know how much time do I have? I have, okay. Now and then I'm going to briefly, yes. Okay, in the previous case, for instance, here, I find the Carnot limit as in the case of usual thermoelectrics. I use the linear response, in this case for the heat flow, and taking into account the affinities with delta T and with omega for the driving. And we work exactly as in your papers for usual. The average of the entropy is different from 0 because you are doing work from outside. So you are generating entropy due to the AC driving. Okay, you can, there are two ways to proceed. One is to look at the problem as a time-resolved problem. This is what you are meant. What I'm doing here is to look at in average. So to consider the average is over one period. Yeah. Yeah, the time resolved is a bit more complicated, yes. So in this case, I'm going to focus on time resolved. And as you will see, there are some subtle things when you look at time resolved things. In this case, what we do is to consider a single quantum dot connected to a single reservoir. Very simple system. This is a single quantum dot, single level, and we are just including the effect of an AC driving, again with the frequency omega. So we have this Hamiltonian for the driven quantum dot, this Hamiltonian for the electrons for the reservoirs, and this Hamiltonian for the contact. And now I'm going to consider a situation where this contact is relevant. So this is not a small quantity. And now the question is how to define the heat current as a function of time in this system. Very simple. As before, I'm going to write the fundamental conservation laws for the energy and for the charge. For the charge, it's very simple. We have that this is the current into the continuum. The continuum is the reservoir, and this is the current into the dot. Both quantities, the addition of both have to be 0 for satisfy the conservation of the number of particles. And this conservation law looks exactly the same if we consider it time resolved or if we consider it after averaged over one period. So in both cases, the addition of these two currents has to be 0. Instead, when we go to look at the energy conservation and we consider the average of the variation in time of our Hamiltonian, we have this quantity which defines the energy flux into the reservoir, this quantity which defines the energy flux into the quantum dot, but we have these additional terms which express the variation in time of the energy which is stored in the contact region between the quantum dot and the reservoir. We also have this term which is due to which express the power developed by the external fields. And the conservation of the energy tells us that the addition of all these terms has to be equal to the power developed by the external fields. So all these fluxes have to be equal to 0 at every time. But it turns out that if we average over time of this, we take the average over time of these quantities, this term here is 0 when under time average. So we only have that in average, the flux into the reservoir, is equal to the energy flux into the minus the energy flux into the quantum dot. And so this term here plays a role only dynamically, only when we consider time-dependent quantities. But now the question comes on how to define, as a function of time, the heat current. In the case of electrons, we usually, and also in DC regimes, we define the heat flux as the energy flux into the reservoir minus this convective term, which is mu times the charge current. But now it turns out that in this, when we look at the time-dependent definition, it makes more sense to consider this definition of heat, where instead of considering here the energy flux into the reservoir at the time t, we include also half of the energy which is stored in the central region. Why this quantity? Okay, we arrived at this definition after making contact between two formalisms. One is green function formalism and the other is scattering matrix formalism. It is something which is not obvious, that it is something which is non-trivial, and we tried to explore it a bit further. So we went to an explicit calculation of both definitions when we consider that our reservoir is at 0 temperature. So when our reservoir is at 0 temperature, we expect and imagine that we are in some adiabatic regime where our driving is very slow, so we are in a situation which is very close to equilibrium. In such a situation, if our reservoir is some big system and in equilibrium, and it is also at 0 temperature, we only expect that the heat can flow from the driven quantum dot into the reservoir. And in fact, we proved that if we consider the second definition, the one which the second is this one, the one including also half of the contact term. So when we consider this second definition, we have this nice Joule law for the heat flowing into the reservoir as a function of the instantaneous value of the charge current. This resistance here is the universal quantum of resistance, which is given by this number. Instead, if we consider the other definition of heat, we find that for some instance, we can have that this quantity gives a number which suggests that there is a heat flow from the reservoir into the quantum dot. So you see, it's a very simple problem, but it is not obvious on which is the proper way to define the heat flow if we want to look at time-dependent quantities. Exactly, yeah, exactly. I mean, what you actually expect is that independently of this nice law, what you expect is that you should get heat flow from the quantum dot into the reservoir. So we show that not only that is satisfied, but it also follows this Joule law, and this is precisely the universal quantum of resistance associated to the contact. So the contact plays the role of resistance.
But then let me ask you this. So different systems may have different contact resistance.
Okay, in this case, we are considering just a one-channel reservoir.
But if you change the geometry, you obtain another prefab. Is this what you're saying?
Yes, in particular, if you consider a reservoir, even an ideal reservoir, but with many channels, you will get, instead of 2, you will get here the number of channels, for instance. Yes. So, do I still have some minutes? Yeah? So I can still tell you about the generalization of the previous problem, but also considering many body interactions. So in this case, I'm going to again focus on the adiabatic regime, and for this, in order to solve this problem, I'm going to use the adiabatic formalism I introduced for the case of the thermodynamic treatment. So now our model is basically the same as before, but now our quantum dot contains also the Coulomb interaction U. And we are again having this AC driving applied with this local gate with a frequency omega, which we assume is small, see? So yeah, it's the adiabatic regime. And we want to make some parallel with this classical circuit. The classical circuit is the following for our interacting quantum dot. We can imagine that we have a sort of capacitor, and the contact term is a resistance, as we discussed a while before. In the case of the linear classical circuit, we will get for the charge here in the capacitor a equation which is very similar to this one, except for the fact that we don't have this integral. This C and R are constant, and we don't have this integral, and we have here just C times V, not V dot. So now I'm going to propose this equation for this classical nonlinear circuit. Now C and R will be quantities that depend on V. V, the amplitude can be large, but V dot is a small quantity. So I'm going to consider this classical equation for this circuit. So now, given this equation for the charge in this part of the circuit, the charge can be calculated by the time derivative, and we get this equation. This equation is obtained assuming that V dot is small. So I cut at the lowest contribution. And now I can apply the adiabatic formalism are formulated before to calculate the charge in the quantum dot. It will have some contribution which is evaluated with the frozen Hamiltonian plus some correction proportional to V dot, which depends on this coefficient. And this coefficient, recall that we can calculate it from the susceptibility given by the Hamiltonian frozen at the time t. This susceptibility at every time t is a quantity that can be numerically calculated very precisely with numerical renormalization group. And so we will apply numerical renormalization group to calculate this coefficient. And now we can get the current, and we can also calculate the dissipation, the power, actually the power developed by the AC sources, which is the quantity, the amount of energy that will be dissipated into the reservoir. We can calculate these two quantities. And this is the comparison with the equation for the linear circuit. To calculate the current, we have to calculate the time derivative in this equation, and we see that this, the coefficient, the capacitance is related to this derivative, and this product of the resistance times the capacitance square is related to this transport coefficient. And now what happens with the energy dissipation? Recall that I mentioned that in the non-interacting case, the power developed by the fields obeyed a Joule law with the universal resistance. Now, let's see in this problem what happens for different values of the interaction U. So this is a small value, bigger, and even bigger. For the small value, what we see is the power developed by the AC fields is very well described by the by this Joule law. But as we increase U, we see that there are two contributions. One which is described by the Joule law, but there is a second contribution, these peaks here and these ones here, which are the effect of pure many-body interactions. The interpretation we give to this additional contribution is the fact that we are, for this value of the Coulomb interaction, we start from the quantum dot in the so-called Kondo regime. In this regime, the quantum dot is occupied, so here is the occupation of the quantum dot as a function of time. So these peaks take place just when the quantum dot is occupied by a single electron. This electron has a spin, and due to the interaction, the spin localized at the quantum dot makes a singlet. This is the Kondo effect with the spin of the electrons in the reservoirs. The effect of the driving is to destroy this singlet. Just in the moment before the singlet is destroyed, some extra amount of energy is released. This something like the energy which was enclosed by the singlet. The singlet is destroyed and it is released in the form of heat of the reservoir. So this is just a summary to finalize. I presented an extended thermoelectric theory to include the effect of the AC driving in systems, in electron systems, which are also under the effect of DC and temperature DC voltages and temperature bias. We have proposed a way to quantify the efficiency of the different operational modes in these systems in terms of new figure of merits. I also discussed the difficulties to define to properly define a heat current in result as a function of time result. And I finally briefly discussed the different mechanisms of dissipation in an interacting quantum dot. So just, I don't want to abuse, but just a short announcement. I would like to advertise a bit this center that was recently created in Argentina, and this is a project in which I'm very much involved. It is a center which intends to work in a similar way as this institute here, to host not only research, but to also host many activities in the form of workshops, research programs, seminars, to have visitor programs. This is the location. This is the center of Buenos Aires, and we are here in the university. This is a picture of the campus. This is our building, which is right now under construction. We are going to have a floor in this big building. This is the status of the construction a couple of months before. It has already almost 5 floors. And this is our provisory location, and I hope to see you there in the near future. Thank you very much. It's it's not, it's related to the frequency.
Should depend also on the amplitude.
Yeah, no,
No? Why not? It's a linear system.
because, yeah, let me, yeah, this. Yeah, because the linear response, this is because of that I started formulating this. Here we are doing linear response not in the amplitude, but in the change of the amplitude, change in time of the amplitude. And because of that is that the effective affinity is this one, I mean, is proportional to the frequency, but it's actually h bar omega divided by t. But yes, so because our small quantity here is b dot, and if you start from other formalisms like Floquet theory, the natural thing which appears there and which renormalizes the chemical potential is this h bar omega.
If I take the omega equal to 0, I still have a drive, right?
Omega strictly equal to 0, you don't have nothing. So you don't have any. It's the constant. You just have the frozen term. So this.
Questions? Okay, let's thank the speakers, both speakers.
Thank you.